Welcome to the presentation on geotechnical considerations on uh, slope stability, ditches, embankments, and detention ponds, 2026. Audience makeup, we have about 280 people RSVP'd. We have a lot of civil engineers across Texas, people from many cities, various municipalities, um, like, county people, and a lot of engineers all around and some developers. So this has got a good cross section of the industry. Want to know about this? This is my contact information. If you need to reach me, my name is David Eastwood. My email is de@geotecheng.com. My number is 713-699-4000. I work for Geotech Engineering and Testing. We've been around for about 40 years. We do geotechnical, environmental materials, and geoforensic engineering. We've got about 60 people, 20 technicians, a bunch of engineers. We work all over Texas, Louisiana, New Mexico, Oklahoma, and Arizona. And we have our own rigs, so we can mobilize on the projects quickly. If you have any questions, you can go to the chat here, I guess, and I'll answer your questions. And let's see. I don't have anything on it right now. This presentation will be on YouTube, so you can go on and watch it anytime you want. I don't expect you to learn everything that I'm going to talk about today. There's a lot of information. There's 2 hours of presentation, or maybe more, 2.5 hours. And so there's a lot of information I'm going to go over, a lot of case history, a lot of stuff that's going around the Houston metro area. So let's see. Your questions, you go to chat and then or Q&A, and I'll answer your questions. We're going to be talking about slope stability. It's a parking lot out here failing. There's a shallow failure out there. You can see the shallow slope failure. This is one of those University of Texas slides I got. This is a TxDOT roadway. You can see the slope failure along the embankment. Here's another one that I got from TxDOT Houston District. They had this roadway, and they got the embankment here, and they have stability problems, and you can see the slope moving. The ground's dropping out there next to the paving. A lot of flood control. Harris County Flood Control, it's got a lot of channels around, Houston area, and with different types of soils, with different types of velocities. So they have a lot of good pictures of some of the problems they have. This is a bridge abutment. You can see that failing right there. Some more bridge abutment. There's another one right there. There's another one here. Global stabilities, slope failure in San Antonio. This is a retaining wall that had a global stability failure. See, the whole backyard failed. They didn't engineer this wall. This wall was not engineered, so they put it up and then it failed. So it took everything with it. You can see that almost 250 houses were impacted. They had to move out. Had to buy back some of these houses. That's another global stability in China. The building just fell down, sitting on piles. They excavated in front of the building and put the fill behind it. That surcharge caused the overloading of the slope and cutting the piles, and just the building fell down. In Conroe, I was out there a few years ago looking at these houses right next to Lake Conroe, and there's a channel in the front here. This channel here, they wanted to deepen it so that water come in, they can put the boats in there, and connected this channel here. And when they did that, the whole retaining wall failed, the whole backyard failed. The whole thing started moving, and contractor didn't have any insurance. It was not bonded, so they had to pay out of their own pocket. So a lot of failures there. This is Leak City out there. I got these slides from one of my friends. You have bulkhead over here that had global stability problem. The slope starts failing out here and moving the bulkhead, and they had all these pool out there in the backyard. Things start separating and cracking and moving. So that was interesting. Landslides, we got them all over the parts of the United States, a lot of them in California. So this is a detention pond out there, and it's got a lot of sand and silt on it. You got the erosion, and the whole thing failed. A lot of slope failures, textile embankments, and channel failures. Here's a failure right there. You can see the slope failure here. Houston, this is a kind of a equipment exit out there near downtown Houston. I was driving there one day and kind of was interesting. Saw the slope failing. The whole lane just came out. Kind of an interesting failure there. They had to go back in and put 2 rows of sheet pile and riprap on top of that. Put the lane back in. This was what it looked like when it finished. So grass start growing on it. Here's some more failures out there near a bridge. Little Cypress Creek. Sinkhole near Greens Bayou. Types of failure, basically, in terms of slow failures, we have deep rotational failures, shallow rotational failure or toe failure, shallow sloughing failure, wedge failure or block failure, erosion failure, failure due to presence of dispersive soils. We have a lot of dispersive soils in Houston area. It's a typical slope. This is a deep failure right there, rotational. As the soil starts moving, there's a resistance here. This is the driving force. The slope comes up. This is a post failure. You got a little mound in here. This is kind of what we call transitional failure. It's basically the slope fails along this plane right there. This is a deep-seated failure. This is a toe failure. That's the toe of the slope. And this is a shallow sloughing failure right there. And this is what we call the wedge failure. The whole thing moves as a wedge. And of course, failures, a lot of the failures we got in Houston area in our expansive clutch is due to weathering. You develop these shrinkage cracks, water gets in there, and soil just starts losing strength. And so you get develop what's called weathering, low strength in here, and the slope starts failing. That's basically a deep-seated failure, rotational failure right there. This is a translational failure. Holding just kind of slides down along a plane of failure parallel to the surface of not minimal depth. Rotational failure is characterized by deep-seated sloughing of a larger soil mass using a circular shape. Again, you can see another one of those things, translational failure. Deep rotational failure, toe failure. That's kind of a deep rotational failure. Shallow failure, rotational. That's this right here. They're kind of like, you can see the deep rotational failure right there. That's kind of what we call block failure, wedge failure. It's a global failure. It's kind of like deep rotational. That's progressive. It fails over here, and if you don't do anything about it, it starts failing over here. If you don't do anything about it, it's going to fail over here. And it's just called progressive failure. It just kind of fails by itself like that. This is a seepage failure where you got shallow groundwater, you got real sandy soils, and this groundwater comes in and, melts these sands. You got zero effective stress and high pore pressure, and the soil starts failing. Flood control infrastructures. We have detention ponds all over Houston area. You got them under the freeways. You go out there, and a lot of these TxDOT facilities, they put the detention ponds directly underneath the interchange or underneath the freeway system. Because they don't have land, so they just put them in there. That's the detention pond right there, Beltway 8. Actually, this is Grand Parkway. I'm sorry, this is Grand Parkway. Yeah. See the detention pond there. If you got drill piers there, you're piling, basically, you got to disregard the skin friction. The skin friction, the piling or drill pier, 5 foot over a non-water crossing area, 10 foot over stream crossing, and in the abutment area, disregard the portion of the foundation passing through the fill. Here, Bower, Hulkley, stormwater detention basins. That's kind of flood control pictures. You can see that this is the Cypress Creek, 81,400 cubic yards of material excavated from the channel. This is a Greens Bayou, $45 million project, 3.7 miles. Conveyance improvements and stormwater detention. There's a detention, basically Glen Forest and Kirkendall. It's Glen Forest Detention Pond. It's Kirkendall. Raised Bayou. That was a big project right there. $400 million between the Harris County Flood Control and Corps of Engineers. This is Huntington Bayou. It was a $65 million project. 8.8 miles of grass line channel. 75 acres of detention basin, 17 bridge replacements. White Oak, that's a big area. That's a $45 million project, channel conveyance. Coal Creek to 1960, 4 detention basins, 2,940 acre feet of storage, 12 miles of linear bikeway. Mason Park project, good old Arch Story Park, Old Westheimer Basin. Geotechnical, so when you get involved in detention ponds and channels, you're gonna have to worry about site geology, fault study, and got to do detailed geotechnical. The whole project is a big earthwork project. You do a phase 1 fault study out there. These are the cracks been in the ground for many years. Cracks can extend a couple 100 feet deep. There's about 450 faults in the Houston area, all the way from Corpus Christi to Beaumont, Houston. They extend about 100 miles inland. So if you go out there from Galveston to Huntsville, there's potential for faulting. Once you pass Huntsville, there's a lower risk of faulting there. They move about half an inch a year. Some of them don't move at all, but then they become active again. This is a fault going through this house here. This is the down-thrown section. This is the up-thrown section of the fault. This is what we call shear zone. If you build Any structures out there, can experience movement and cracking. That's the down thrown section. It's the up thrown section. It's the lineation of the fault going through this house. It's the house sitting on top of the fault. It's Carlton Woods. This is a fault there. That's a bump in the road. That's where the lineation of the fault is going. This is post-Stoke area. You can see the fault there. You can see the fault right there. This is the up-thrown section. This is the down-thrown section of the fault. The fault has got an up-thrown section, down-thrown section. This is the area that's dropping. These are the soil layers. Like this is clay, sand, and clay. As the soils drop, stratigraphy of the soil gets out of whack. You can do borings out here and resistivity. And from that, you can determine if the lineation of the fault is over here and where the scarp is. Here's the aerial photo as part of the phase 1 fault study. We'll look at the aerial photos. You can see the lineation here, cracking the paving here, going towards that structure right there. Again, you see the lineation here. This is the down thrown section. Lower area, there's more moisture, so it's darker, more grass. It's the up thrown section. See the lineation here on aerial photos, the down thrown section, up thrown section. You can see the lineation of the fault here, Greens Point area. Oh, it's the down thrown section, up thrown section. Now we're developing all these land around Houston area. And these sites are wooded, where they got tall grass. You can't see the lineations. So you use LiDAR map. LiDAR uses laser light to measure the distance. And from that, you can calculate where the change in elevation is taking place and evaluate the lineation. That's a LiDAR map there. And they put a bunch of condos over here, and they found out they had faults. They didn't check for faulting, so they had a lot of problems. If site is wooded and has got tall grass, you may have to hydroax the trees and mow the grass, but you cannot change the elevation. So don't use a dozer. You hydroax, and then you go back and check the elevations. We got faults all the way in Houston, Dallas, and San Antonio, and Austin, but those cities, their faults are not active. Ours are active. These are the faults in the Houston, Beaumont area. These are some of the fault maps. Doesn't show all the faults, but you can see some of the faults in Houston area. Some more fault maps. You can see the bill. This is 610. This is Beltway 8. I-45. More fault map. You can see the 610. Beltway 8. And here's a fault map there where it shows a 610 here. Down thrown section and long thrown, up thrown section here. The tech mark shows the down thrown section. And we have faults in our library that are not on these maps. A lot of the owners and developers don't want us to disclose where the faults are. This is a track in out there in Pearland. Pearland's got a lot of faults there. And you can see the Macoa Salt Dome there. A lot of faults. Here's the track. This is a pipeline. You can see the fault clearing going through this track. So we told the developer, well, you have to develop this area into either a linear detention. This is what we call hazard zone. About 130 foot wide. It's a hazard zone. Turn into a linear detention or park. Can't build houses here. Some of the stuff that you worry about, any kind of a development where you're going to have detention ponds and, channels, you got to look at the existing structures, vegetation, any kind of a bridge that you're going to put in there or you have that may cause damage. If you put, widen the detention, impact on proposed facilities, erosion, slope failures. So We get involved on projects when there's channels or detention ponds. So we send our rig out there and do borings out there. This is a buggy rig. That was a truck mounted rig. This is a truck mounted rig, and this is a buggy rig. This is a truck mounted rig. It's a truck rig go out there on the channel. Sometimes we use our portable rig. We do borings at the toe of the slope because the soils at the toe of the slope may be different than the high bank. There's going to be more sand and silt deposits here. So you do borings here and borings at the top as well. Most of our sampling is taken with what's called a Shelby tube sampler. This is a 3-inch diameter tube, hollow. You hydraulically push it into the soil. You get a soil sample. You look for root fibers in the soils. The root fibers tell you the depth of movement active zone. Well, actually, the active zone, that's a zone at which soil experiences shrink and swell movements. That's important to know. You know, for example, the depth of your shrinkage cracks in your soils, and the root systems from trees extend to the areas where there's oxygen and water. And when there's not, they stop having root fibers. So as you go deeper, the root fibers end. In the areas the soils are sandy, we run the standard penetration test. TxDOT is not requiring S.P.T on their borings. That's 140-pound hammer drop 30 inches. So S.P.T here, 140-pound drop 30 inches. You drive into the ground 18 inches, 6-inch, 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 and you count blow counts. It's a 140-pound hammer dropping 30 inches. That's a split spoon sampler. That's a split spoon sampler. You look at the blow counts. You disregard top 6 inches. The first 6 inches. Blow count 0 to 4. Your soils are very loose. Between 5 and 10, your sands are loose, medium dense, 11 to 30, 31 to 50, dense, very dense, above 50. Start going deeper, you're going to hit rock. That's limestone here. So if you guys are from, I know we got several people from San Antonio. You got, limestone, and start going deeper, you're going to hit rock. Texas cone penetrometer, if you got a project, TxDOT back in the old days required Texas cone penetration test, which is a 170-pound hammer, drop 24 inches, driven 12 inches, seating, and then 6 inches and 6 inches is a 3-inch diameter cone like this. There's the cone like that. It's good for rock, not for soil. So if you're in Dallas, San Antonio, and Austin, where you're going into rock, you want to know if you got rock, how strong it is. TCP is good. You drop it into the ground 24 inches. You measure the blow counts after the first seating 12 inches. That's the 170-pound hammer. So if you run the S.P.T, for example, that TxDOT is required, if your standard penetration test is less than 2, you got very soft clays. Okay? If it's 2 to 4, you got soft clays. That's a shear strength of about 0.125 to 0.25. Between 4 and 8, you got medium and stiff. That's 0.25 to 0.5. And that's a stiff. Blow counts from 8 to 15. Strength between 0.5 to 1.0. Very stiff, 15 to 30. Of course, if you're doing a TCP, 40 to 80. And if it's like greater than 60, you got, pretty hard material out there. Let's see if you got any questions. Okay, we don't have any questions. Yeah, I don't have any questions. Now, if you're in rock, um, you got an STP greater than 100. You got very hard rock. STP, SPT, above 100 blows. You got 1 inch over 100 to 5 inch over 100 TCPs. You can have siltstone and shale. That's hard rock. If your SPT again above 100 blows, got moderate to hard soils, and with your TCP of 2 inch over 100 or 5 inches over 100. Soft, if your SPT is 80 to 100, you got soft rock. And if your SPT is below 80, you got very soft rock. Could be shale. So this is kind of some of the stuff that from TxDOT. This is a correlation between TCP and soil shear strength. Shear strength is equal to 300 plus 60 times blow counts of the TCP. So if your blow counts is 6, your shear strength is 660 PSF. Again, we're not using TCP anymore, but if you got rock, you want to know how strong your rock is, you can use TCP. After you do the borings, you cut the samples at the end, you put them in foil, you put them in a wax box and plastic bags, keep the moisture constant. You would have to test the soils right away. You don't want it to dry up. You look at the groundwater. We don't get a good reading on the groundwater. Groundwater fluctuates quite a bit, and the borings are not very good indicator of where the groundwater is because it takes time for water to come in, especially with clay soils. So regular groundwater, your groundwater in Houston could be 30 feet deep. In San Antonio, it could be 60 feet deep. And it depends on the season. If you're in the February, like right now, your groundwater may be shallow because of all the rainfall, although we're in a drought. And then if you're in August when you have no rainfall hardly, your groundwater can be deep. The best way to measure groundwater is to put piezometers in. A lot of times the project budgets do not allow that. But the borings, from actually doing borings, then trying to find groundwater is not a very accurate way of doing it. A lot of times borings do not show groundwater. The way you measure groundwater, you get a tape measure with a weight at the end of it. You throw it in the hole. And when it goes plump, that's where your groundwater depth is. CPT, got it. Cone penetrometer testing. If you look at the Harris County Flood Control Design Manual, they say you can use CPT, Texas cone penetrometer testing, which is a cone. It's about 1.4 inches in diameter and can go up to about 100 feet. That's the cone, about 1.4 inches in diameter. That's the tip of it. That's the sleeve right there. That's the device like this. You hydraulically push it into the soil. You got a truck, use it as a reaction weight, and that's the cone right there. Here's the cone right here. You jack up the truck, use it as a reaction. This is Louisiana. Here's the cone right there. You push it in. Here's your cone. You push it in like that. Here's another recent project we did. We had to use cone right there, like that. This is Louisiana. See the cone right there. Jack it up right there. This is inside of the truck. You hydraulically push the thing into the soil. These are the rods right this, like that. You hydraulically push it in. So you use the truck as a weight reaction, hydraulically push the cone all the way down. This is the tip, this is the sleeve. This is the tip, this is the sleeve. It's the tip, it's the sleeve. It's got the instrument on it. It's continuous soil stratigraphy definition, identifies thin seams and layers, estimates geotechnical and hydrological properties, F.ASCE, and no drill cuttings. So you measure the friction on the sleeve, tip resistance. So you go down here, you hit a sand layer, it goes up. Got clay layer, sand layer. hydraulic conductivity, pore pressure. This is geostatic stress. This is the ratio of the sleeve over the tip in percent. And this is your soil stratigraphy based on correlations. Here's that shows the relative sleeve friction, tip resistance, pore water pressure, friction ratio, soil stratigraphy, shear strength, friction angle for sandy soils, so it's clay soils, and it's the SPT correlated values. A lot of data. So if you want to know what kind of soils you got a friction ratio of, let's say, 5%, and you got a cone resistance here about 1. You go over here, you got an area 3. So in this area, you got clay soils. That's how you classify it. Most of the geotech work that we do in Houston area for flood control, we follow Harris County Flood Control District guidelines. If you're doing geotechnical work for developments, we don't follow the geotechnical guidelines by Harris County unless that development is going over a flood control channel or somehow related to Harris County flood control. But if you're doing stuff in Montgomery County, Galveston County, or Brazoria County, unless, for a private developer, you don't use the geotechnical investigation guidelines for Harris County flood control. There's also City of Houston geotechnical guidelines that refers to design of detention pond and channels per the Harris County flood control. That's Harris County Design Manual that refers to Harris County flood control for geotechnical guidelines for detention ponds. Now, if I'm doing a job for Harris County or Fort Wayne County, I use Harris County flood control guidelines because that's what their manuals require. TxDOT, they really don't have any kind of a guidelines on detention ponds. They really just depending how they feel. They tell you got a big detention pond, go just do 2 borings, kind of very limited investigation when TxDOT does their detention ponds. Not much of engineering. Laboratory testing. One of the tests we do in the laboratory called liquid limit test. In this test, we want to know how much water we should add to the soil to behave liquid. So you put soil in here, add a lot of water to it. When it becomes liquid, you put in this cone and cut a groove through it. You turn this handle 20 to 30 times. When the groove closes, you get a sample of that. You put it on a scale. You get wet weight of it. So we want to know how much water is in the soil for it to behave liquid. Then you put it in the oven and dry it up. And you dry it up, you get a dry weight. You find out the amount of water. Basically you get the wet weight minus dry weight. And then the plastic limit, you want to know how much water is in the soil for it to behave semi-plastic, called plastic limit test. You roll the soil in 1/8 of an inch. You get the wet weight of it. You put it in the oven and dry it up. And you get the dry weight. You get how much water in the soil for it to behave semi-plastic. So if the difference between liquid limit and plastic limit is called plasticity index, PI. So if your PI is less than 20, you got a soil with low soil potential. Between 20 and 30, it's got mildly expansive. Between 30 and 40, it got highly expansive. Above 40 is very highly expansive. A couple other tests you do in the labs called the hand penetrometer and a torr vane. In a hand penetrometer, you take the soil sample, you push it into the end of the soil. You can read it here, what kind of strength you have. Torr vane, you get that torr vane. You put it at the end of the sample, sure the torsion, and you can read what kind of strength you have. Unconfined compression test is another test we do. You take a soil sample, you put it in this machine. You got a proving ring, you got deflection, dial gauges. You crush the soil, see how much load it takes to crush that soil. It's called unconfined compression test. That means it's unconfined. There's no lateral pressure on it. So if you want to get a little more fancy, you get undrained UU test, unconsolidated undrained test. Basically, oh well, this is unconfined compression right now. There's no lateral pressures here. It's sigma 3 0, and that's the soil shear strength. It's a normal stress, undrained shear strength. This is the shear strength right there. Advanced testing, unconsolidated, undrained test. You put the soil sample, you put lateral pressure on it. That kind of similar to what the soil experiences in the ground. Let's say you are 10 foot deep. You put 1200 psf lateral loading on it. It usually gives you higher strength. And this is a lateral pressure equal to the geostatic pressure. This is the actual loading to shear the soil. This is a total stress test, and that's the undrained shear strength. This is the strength in here. The phi is 0, phi angle. Triaxial test. This is our triaxial test setup. This is the cell. You put load on the sample equal to the geostatic stress, and you shear it and develop what we call total stress envelope, and uh, measure the pore pressure, and from that you get the effective stress envelope. So that's C and phi for effective stress. You will use that for long-term slope stability analysis. This is a typical stress strain curve. That's the strain, that's the stress, and that's for 3 samples. Oh, this is the envelope, more envelope. You can see the total stress and effective stress. C14, phi of 10 degrees for total stress, for effective stress. Um, C is 1.173 psf, phi is 22 degrees. So what we have when we shear the soil, you got the undisturbed peak value, and then we get fully softened, normally consolidated peak. Undisturbed soils, peak value strength, and fully softened soils that we use for slope stability. We use fully softened soils. This is kind of a correlation between the PI and the soil shear strength. So if your PI is 60, your phi angle is about 25. There's another correlations here that shows that if depending on your soil liquid limit is 40. Uh, your phi is about 25 or something like that, 24, and that shows your shear stress. So depending on normal stress, you can calculate, see that what your shear stress is for C and phi values. That's your C value for long-term analysis. We also use this fully softened shear strength in soil parameters, representing long-term shear strength in stiff clays that we got in the Houston area. This is over-consolidated clays that we have. We use a fully softened shear strength. This numerically is defined as the peak drained shear strength of a clay uh, in its normally consolidated, reconstructed state. The reduction from peak to fully softened strength occurs over time due to wetting and drying cycles. So if you look at the PI, this is the strength values from a fully softened. If you want to be really conservative in your slope stability, use the residual strength. That's lower. That's higher strain, and you got a real lower strength soils. Gradation tests. We run gradation on soils to classify them. There are sand, clay, and silt. These are sieves. You put soils in there and shake them, and you get a gradation like this. Here, number 200. Okay, it's about 66% passing. This is sandy lean clay. Here's another one. There's a lot of gravel in here. For number 200, 20% are smaller. So most of it is in coarse aggregate and coarse sand. So this is kind of like a base material. Gravel, the size of a gravel, usually less than 3 inches in size. Sand is less than 0.187 inches in size. Clay is less than 0.0029 inches in size. These are typical what we call the Harris County flood control boring logs. They like it to be like landscape like this that shows silt and sandy lean clay. They got sand in here. Here are the SPT values. These are pocket penetrometer values. And you can see in here blow counts. This is the Atterberg limit stuff, the moisture content. So here's the soil liquid limit and PI. And if you run a triaxial test, this is a CU test. And C prime and P prime are 160 and 21. C and Phi are 160 and 21. So here's another one here. You can see soils. We got the SPT values that he had this depth. And also we got a TCP values. TCP for textile is 100, TCP 100 here. Got the sandy lean clay, fat clay, TCP 100. So it's got that very hard. So very hard soils. Dry densities in here. You got the moisture content, liquid limit 47, plastic limit 18, PI 29. Dispersive soils. We have a lot of dispersive soils in Harris County. These soils are soils that are easily erodible. You hit water, they erode when they get wet. They contain a high percentage of sodium ions. Um, you can see in channels these holes, they call them jug holes along the channels where they get eroded. A lot of erosion due to dispersive soils, jug holes. You can see that this is basically embankment here. This is a detention pond. You got failures here. Failure due to dispersive soils. This is a project out here, Veterans Memorial and Beltway 8. They had a lot of dispersive soils over here. They had these holes in the ground. One of the cops was chasing somebody. He fell into it, broke his back. So they sued everybody. We had to go in there and figure out if the soils was dispersive, which it was. There was nobody checked it and to find out if the soils were dispersive on that site. Crumb test is one of the tests you run. Just find out if your soils are dispersive. You get 3/8 of an inch cube soil sample. You put it into water. If it's clear, the soil is not dispersive. If it's cloudy, your soils are dispersive. Pinhole test is another test method that uses basically determines the dispersivity of the soils. Basically, you get distilled water under a hydraulic head of 2 inches, and throughout the 1 millimeter diameter hole that you punch through the soils, you put the soil sample here, you punch a hole in it 1 millimeter, you got a head of water, and water comes out of it through that hole. If the whole water is clear, the soil is non-dispersive. If it's cloudy, it's dispersive. They got a rating technique. If a rating is D1 or D2, the soils are dispersive. If it's ND1, soils non-dispersive. Rating of ND2, ND3, or ND4 indicates the soils are slightly to moderately dispersive. Some defensing measure may have to be incorporated in the design. Another test that like I know Harris County Flood Control likes is called double hydrometer. These are hydrometers. You run one of them with regular water, the other one with sodium hexametaphosphate. It's a dispersing agent, and basically you run two separate hydrometers. one for natural and one with the dispersing agents. And you plot them. This is the with dispersion. You can see a lot of fines are going through. It's a number 200 sieve here, and this is a without dispersion. You get the ratio in here. Basically, you get a ratio of the clay of 0.002 millimeter without dispersion over clay size of 0.002 millimeter with dispersion multiplied by 100. That becomes your percent dispersion. So if your percent dispersion is less than 30, your soils are non-dispersive. Between 30 and 50 is intermediate dispersive. Above 50 is dispersive. So percent of dispersion soils greater than 50, the soils is probably dispersive. If it's less than 30, the soils is probably non-dispersive. Between and 30, soils are moderately dispersive. You run other tests to make sure if the soils are dispersive. How to repair sites that channels or detention ponds where you have dispersive soils. You remove the dispersive soils and you put in non-dispersive soils. That's one way to do it. You remove it and replace it with non-dispersive soils. You can lime stabilize the soil with lime and put it back in, remove it, lime stabilize it, put it back in, the soils become non-dispersive, or you put a clay liner on it. So if this is natural soils, you put a liner on it of non-dispersive soils, and the soils become non-dispersive. When you do channels, one of the ways you can reduce erosion, you put basically a back slope channel on it. So if this is your channel in here you put a swale there. So this is a detention pond here. You put a swell in the back of it with a outfall. The water comes here and it goes in the channel and doesn't flow over the slopes to call it eroded. You can see our detention pond here is the back channel in here, and the water doesn't go over the slope. And you got basically an outfall in here. Here's another detention pond in here. You can see they put in here a swale behind it, and you got an outfall in here. Piezometers to measure groundwater levels. Like I said, regular groundwater, regular borings, they don't give you accurate measurements of the groundwater. Most of the times we don't hit any water. And so the way you measure water level is using piezometers. These are PVC pipes, about 3 inches in diameter or 2 inches in diameters. And they're slotted. Water allows to flow through it. It's called piezometer. You put them in the ground, these PVC pipes. And you put sand around this screen. Usually you put 5 to 10 foot screen in there, put sand around it. Above that, of course, you put bentonite balls and then cement grout on top of it. The way you measure the water level, you put a tape measure with a weight on it, and you throw it in the piezometer. When it hits water, it goes plumb. You might measure the water level. Here's the piezometer in the roadway. They're going to have storm sewer sanitary lines. You put piezometers in. A typical construction of piezometer, you got the screen in here. You put sand around it. Above that, you put bentonite seal pallets. And above that, you put cement sand grout all the way to the top. That's the piezometer sticking out. Geotechnical engineer should work with the surveyor. When you do borings for flood control, for example, you need to have all the GPS data and elevations. These are some pictures of the houses that are failing on slopes near Buffalo Bayou. Go out there and look at some of these houses. Some of these houses are built near the bayou. The foundation systems are not adequate. The piers are not deep enough. It starts moving and the slope starts moving and failing. This is one of the houses sliding down the slope. This is a house in Tomball. I was looking at a ditch that was failing. Trying to buy the house back. So if you build, structures on near a slope, you got to have to check for slope stability. May have to put retaining walls in or deep foundations. This is the columns for some of these houses on the slope. Column slots moving and cracking because of the deformations, landslides. This is a house out there in Arlington Court near Memorial Park. Notice there's not much space here between the houses. The backyard patio was moving. You can see the foundation here, the column tilting. They would put concrete bags in there that made the slope heavier. And that was the retaining wall that was initially putting that was not engineered. So the patio starts moving. So we told them you can't get any equipment back there. Just sell the house as is and get out because eventually with time, that patio is going to fail. There's a house in Memorial here for this doctor right there we were looking at. Backyard was tiered like this. That's Buffalo Bayou tributary here. It starts moving. The slab on the house starts cracking. I had to tear down the whole house and build a new one. Slope stability was not considered in the design of the house. Global stability, when you do buildings or structures next to a slope, you got to check for global stability. If these are your foundations, you got to check the stability here. Otherwise, your slope starts failing and your structure is going to go with it. Here's a global stability for sheet pile walls. You drive sheet pile walls on the, Port of Houston or, near a channel. And, so you got to check for global stability of it. This is the sheet pile wall here. This is the anchoring system. Global stability, make sure you got at least adequate factor of safety against short-term, long-term, and rapid drawdown. MSC walls, if you got MSC walls, you got to check for global stability for these guys. Otherwise, they're going to fail. So you check for stability and, bearing capacity and settlement of the MSC walls. This is 288 project, by the way, near 610 Loop. This is some of the embankments for some of the bridges settling. So you got to check for bearing capacity and global stability. The way you model, you put the MSC wall in here, you put your soil layers in, you put the groundwater, and we put the water right there at the top and run slope stability on it for short-term or long-term. You need to have a minimum factor of safety of 1.3. Slope repair, if this is your channel in here, and if it's failing like this, you go on repair it, remove all the failed areas and rebuild it like that. You can see the slope failure in here is rebuilt like this. If you go on back and put a bunch of fill on it, when you do slope stability analysis, you got to use remolded salt shear strength for slope stability in the fill. Slope stability analysis, Harris County Flood Control says if you have grass lined slopes, usually like to have 4-to-1 slopes for channels. Although we do a lot of channels with 3-to-1 slopes. Concrete lines, slopes, 2-to-1 or flatter channels. Yeah, you never put anything concrete line slopes with less than 2-to-1. Grass line slopes, 3-to-1 or flatter for detention basin. When we do full slope stability analysis, we do end at the construction. We use what's called total stress. As soon as the construction is over and all that, the soils they don't have pore pressures, and so use total stress method. And then with time, use what's called the soils go through weathering and stuff like that. Use fully softened soil shear strength. Uses effective stress with pore pressure. That's when the soil changes, becomes fully softened, and where you're going to get the slope failures. Rapid drawdown is when the water in the channel or detention pond goes all the way to the top and it drops quickly. It develops pore pressure in the soils, reduces the soil effective stress. So these guys are sitting out there next to the channel here. It starts raining. The guy's a gator. Water's coming in. They're still sitting there. The water's coming up. The gators are here, alligators, and they're just still sitting there watching. Water comes all the way up. They're still sitting there. Then it goes down all of a sudden. The slope is all saturated, and as it does that, the slope fails because the soil gets all saturated. It was not designed for rapid drawdown. There was no geotechnical report done, so the whole bulkhead fails. They sue everybody, but a lot of the flat work. Here I'm out there taking pictures. Bulkhead drops. So when we do slope stability analysis, we do for short term, long term with pore pressure, or fully softened, rapid drawdown with pore pressure, no time for drainage. The factor of safety we're looking for are 1.3 for short term, long term, but 1.5, rapid drawdown 1.25. Here's a short term analysis. This is the groundwater right there. This is the soil layers. You model the slope geometry and see what it does with total stress soil parameters. You got a factor of safety of 2.9. You do long term, fully softened. You got a factor of safety of 2.2. Rapid drawdown. Essentially, water was here and then it drops to here. The slope is all saturated. You got high pore pressures there. Rapid drawdown, you got a factor of safety of 2. Here's the outfall failure. That's the Tidwell Street. A lot of these outfalls, they don't have good compaction around them. A lot of sandy soils. They just got to wash out, especially if there's a leak. It starts failing. You're going to have to go clean up the mess. Just put cement stabilized sand around it, putting a new pipe, and then backfill it. Put grass on it. Windermere Outfall. This is Buffalo Bayou. The whole outfall failed. A lot of silt in here. There's no access to get to it. Manhole. A lot of silt. The bulkhead is moving. That was the access right here between two houses. We told them to go back in there. If this is your pipe, you can put cement stabilized sand around it. You put it in and put either or bull rock with it, or just go with cement stabilized sand. That's the top view. Is the side view. Here's when we have just cement stabilized sand with no rock and fill on top of it. That's the pipe. That's the top view. CSS. Channel repair technique. I mean, if you look at this video in here, you can see the slope, trying to repair them in here. Also putting a slope paving here. Yeah, put the base in here with rock, and you can start building the pad on top of it, and then basically grade it. And here's they do the slope paving. If you notice, they put the concrete from top to the bottom when they pour the concrete for slope paving. Here are some slope failures in here along the channel. Gonna have to go out there and remove all the loose materials, build your base in here with rock. Then you're gonna start building your pad, and you slope it, and then you put some clay on top of it for grass to grow through it, grow on it. Grass will go on. Channel repair is another project here. Channel repair. Here's kind of flood control you like to use is rock. They put them like at 15-foot spacing. These are 4-foot little slivers of rock. You put the base in there and you put soil on top of it. So you build it with rock. Again, here's a channel in here. You put the slivers in here, put fabric underneath them, put rock on it, put clay on top of it. Here's another channel stabilization. You demuck it, get this stuff out, soft spots. You bring in rock. You put rock on the channels, cover them with clay or structural fill, allowing the grass to grow over them. Here's another one, channel stabilization. You put a lot of rock in here. Rock is not cheap. Trying to grade it, compact it. Got the rock here, and you put clay on it. If you go out there in Fort Wayne County and look at a Stavanoa Bridge, Fort Wayne County, it's a very interesting project. I'm going to put more on that the next presentation, but I was out there looking at it. Stavanoa, this is kind of a turn in kind of meandering of the uh, river, and you can see all the rock that they use, and they drove sheet piling here. I presume they drove it to slow down the flow of the water, but they dress up the whole thing with rock. You see the riprap there, the channel stabilization. Here's the job here, a small channel for a commercial facility, offices. You got the detention pond. It's a parking lot. They go out there. They got the outfall. Here has the parking lot. Allow the sheet flow come over here. They put rock in here so the water goes in the channel, in the detention pond, so they don't have that not much erosion. Brazos River, they got 40, 50-foot tall, sandy, silty channels out there in Brazos River out there. You go look at it in Fort Wayne County. A lot of erosion. Usually you lose about a foot or so a soil every year here because of the erosion and failures. So there was a project and they went out there and put rock out there and they put a rock toe on it to stabilize this area. You can see the subdivision in here. See the rock there? They got a rock toe, and you got areas where the rock is just coming in, allow the water to come out over sheet flow over it. That's the toe. See the toe that built it up with rock. Buffalo Bayou. That's a kind of a golf course out there on San Felipe. Go out there and you can see this Buffalo Bayou embankment. They put some uh, some some materials over here for erosion protection, and they didn't do a real geotechnical study of the slope over here, so they got a bunch of rainfall. The whole thing start failing. The slopes start failing out there. Buffalo Bayou. All this matting material comes out. That's the golf course over there. A bunch of attorneys walking around. Slope failure. Red line here. You cannot play golf past the red line. That's me. So we put some inclinometers here that measures the movement of the soil. See where the failure surface is. These are the inclinometer. These are the inclinometers in the slope, one in here, one in here in the embankment, and find out where the slope failure is, where it's moving. That's basically PVC pipes. That's the inclinometer. You put them in the hole, move it up and down, and you measure the movement as a function of time, and you get cumulative displacements. So these are the different times of the year where you go measure, and you can see the movement here. It started about 4 meters. Here about this inclinometer about 3 meters. Here's about 3 meters. So about 9 feet or so. That's the bottom of the slip circle. So really good, interesting stuff. And that's the meandering of the Buffalo Bayou. There's a house right here. It's a really interesting project. Recommendation was to go in there along the embankment of the failed slopes, go in and put some drill shaft walls in there to stabilize the slopes. Not the cheapest solution, but that's what the recommendation was. Detention pond. This is a detention pond in Brazoria County. In 2017, after Harvey, the whole thing starts failing all the slopes, all the erosion problems we start developing out there. They were building the detention pond. The whole thing starts having erosion problems and slope failures. All the outfalls from the subdivision fell into the detention pond. They start failing. Outfalls number 1, number 2, number 6, number 5, number 4, number 3, number 1. They all broke down, starts falling. We did 5 borings out there to get the soil stratigraphy. We had like about 15, 20 foot of clay. Below that, we had sand and sandy silt. That was a typical detention pond design. 3-to-1 slopes below water, well, 4-to-1 above the water. So we had to go back and find out why it failed. We ran a slope stability by calculating the soil shear strength for lean clay and silt we had out there. We came up with C and F angle of 150 and 14, for factor of safety of 1, and 0 and 24 for the silt. We recommended at the outfall area put 10 foot of cement stabilized sand and put the outfall in there and put cement stabilized sand on top of it. And then go out there and put 2 foot of cement stabilized on-site materials, cement stabilize it underwater to kind of stabilize the whole thing. Now, they thought I was too expensive to go out there and put 10 foot of cement stabilized sand around the outfalls. That's various outfalls, number 1, 1 to 2, number 2, number 5, number 4. We recommend stair-step technique, going out there and basically cement stabilizing the on-site sand and silt all the way at 1 foot intervals lifts. That's what the recommendations were. PCA, Portland Cement Association. It's called stair-step slope stabilization. You put them cement stabilized with 8 foot wide, 1 foot thick lifts. We checked the soils. They were just sandy soils and silty. We add cement to it, try to find out the right amount of cement to it. So we added cement at various percentages to the clay and the sand and silt and tested them. We ran proctor tests, and the sandy silt was the red one and the blue one was the clay. On the job site, we ran the proctors on them, and we stabilized them with sand. We ran the string test, and we got values of about 165 psi, all that for clay stabilized soils with cement. We did the same thing with the sand and silt, and we got 138, 134. So the soil became really strong when you stabilized them with 8% cement. So they didn't want that. So what we did was we said, okay, how about putting just 1 foot of cement stabilized, going there and stabilize top 12 inches with cement on-site soils and to stabilize the slopes. They said they don't want to do that. So they ended up stabilizing only 1 foot above the water level, not underwater. This is a stair-step technique recommended by PCA on stabilizing slopes using cement. You put them in lifts and compact them, 1 foot layers. The actual thickness comes out to be about, the outer normal thickness and inner normal thickness. So if you have a 12-inch lifts and your slopes are 3 to 1, let's see, 3 to 1, your thickness actually is 2.7 inch for outer and 2.5 feet for inner level. So it's a really good way to stabilize slopes. It's kind of expensive. It's a 3 to 1 slope. Or you can do what's called plating method. Just stabilize 12 inches a top layer of the sand and silt and clay. You go out and mix it, cement with it. You compact it. That's plating method. They ended up putting cement stabilized sand around the outfalls. Compacting it. I was driving on US 290 out there to Austin, looking at the slope failure here near Brenham. The whole thing starts failing. The concrete paving and all that failed with it. Yeah, when it did, it's soil nailing to stabilize it. They drill holes in the soil and put nails in it. There are the holes right there with the centralizer with steel in it, and nail it in, put grout around it. These are the soil nails and put facing on it. Shotcrete with the wire. So that's what it looks like. Areas to stabilize in terms of the slopes. Buffalo Bayou is really nasty because of all that sand and silt. Brazos River is nasty because of sand and silt. San Jacinto River, Trinity River, and Cypress Creek areas. So Brazos River got these high, very tall slopes with sand and silt. San Jacinto River, they're not as tall, a lot of flooding problems. Buffalo Bayou, you got, slopes of 10, 20 feet tall. Lots of sand and silt out there. Channel failure stabilization. You've got channel stabilization again. Of course, you can use rock there for some of the stabilizations. Or you can go out there and put blocks in there, block walls coming in, and concrete lining. You have a lot of money. Or you can do in some areas, put concrete lining out there in your channels. The concrete lining, and you got a toe in here. Bayou channel stabilization. This is the kind of a cheap way of doing it. Some of these private contractors, when they stabilize some of these houses out there on Buffalo Bayou, they go out there and drive these channels in the ground, and they put wood lagging in here, and they stabilize them like that. They don't check for global stability or anything. That's how they stabilize. It's cheap. You can use geogrid stabilization. You go out there and remove the soft spots, and you lay down geogrid in the slopes. That reinforces the slope. It increases your factor of safety. That's the cellular mattress. So you lay them down there and you reinforce your slopes. Erosion protection. This is the tire protection. It's used in some of the countries, I guess. Tire stabilization. Geotechnical engineering should be provided with channel velocities, dispersive soil characteristics of the on-site soils. If you got a grass line channel in sandy soils, you can have feet per second. If it's grass line, 6 feet per second. You can use riprap there. You can have velocities as much as 8 feet per second. Riprap gradation 2, 10 feet per second. Articulated mat, 10 feet per second. Concrete line, 12 feet per second. These are some of the erosion areas that you see on some projects. Use the grass, the cheapest way to go on the slopes, as long as placed right. Lasts very good. Grass is great. Matting, if you got a lot of erosion, can you be using matting to allow the grass to grow? So you go put the matting on your channel, on your detention ponds. Allow the grass to grow. Matting there. You basically put nails in the matting, keep it in the ground. Allow the grass to grow through it. Riprap, we got 2 types of riprap that Harris County Flood Control has, and one of them is bigger than the other one. That's grade 1 and grade 2. Use 18 inches thick riprap mat is used. Grade 2, when 24-inch thick riprap is grade 2 is larger than grade riprap grade 1. Here's a riprap here at the outfall. Usually put fabric underneath the riprap. Keep the fines in place, otherwise the fines may leak in between the rock. There's a detention pond here. Here's basically a bend in the channel where you put riprap there on the slopes. The grass will grow through them. Concrete lining. I don't know what happened. Concrete lining. If you go out there in Sims Bayou out there, near Westview area, Bel Air, a lot of concrete lining, a lot higher velocity channels. It's a bridge. You got concrete lining here next to the bridge. Don't put concrete lining on slopes steeper than 2 to 1. This is a 1.5 to 1 slope with concrete lining. The whole thing failed in near Space City Boulevard, Bay Area. It was a litigation on this case where the whole concrete lining failed. Too steep of a slope. Slope paving, poor maintenance. Looking at one of these projects, they had the concrete paving, slope paving on them that allow all this vegetation to grow. Nobody maintained it. Nobody cleaned it. And the whole thing failed with time. Lots of void underneath it. A lot of erosion. Raymond Ville concrete channel failure. Go out there, you see all the vegetation growing, all that trash. A lot of voids underneath the concrete. Slope paving construction. When you do a slope paving, you go out there and pour your base first. You put your steel in, compact that subgrade, 95% of standard Proctor density. You start pouring that concrete in, you establish your base. You clean up your slopes, you grade them. You put your steel in it, start pumping the concrete from the top. For the paving. You put in your weep holes. With time, these weep holes get filled up with trash. They don't work to relieve the hydrostatic pressure. Concrete canvas. That's something to think about. These are about them 1-inch thick canvases. You just roll them up and just lay them down on your channel as erosion protection. Basically, you got a concrete layer here, dry mix concrete. Basically you got a surface here and a PVC backing. You just roll them in your channels for erosion protection. They're cheap and fast. Articulated mats, kind of expensive. You can use them for erosion protection. Your grass will grow through them. They're nice. The green option, you lay them down like that. That's the detention pond in Katy area. You can see they're connected together with wire. They got fabric underneath them to keep the fines in place. Gabions is a very good alternative for erosion protection. Also, retaining wall system. They both have retaining wall and erosion protection. They're a green option. Grass will grow through them. Basically, it's a chicken wire, bunch of rock in it. You can specify what kind of wire to use and how long it's going to last. That's what it looks like. Got these bins, you fill them up with rock. You can see them like this. This is a Southwest Tennis Club out there near Memorial area. See the gabions used. Cement stabilization of the slopes. This is Bay City. That's the nuclear plant out there. They got a huge detention pond there, and they stabilize all the side slopes here. They got clay with cement. It's been there 40 years, doing real well. On this other side of the channel that's not next to the water, they just use grass. Detention pond is the Art Story Detention Pond. Fairmont Parkway, Westheimer. Number of borings for detention ponds. Flood control requires a minimum of 5 borings to be drilled in the first 5 acres, and one for every additional 5 acres. That's the inwood forest construction of the detention pond. Here's kind of flood control. So you dig out all the soils of the detention pond, establish good side slopes. That's the Bay City with cement stabilized sand and cement stabilized clay for erosion protection. That's a textile detention pond out there on Beltway 8 and I-10. Got a pilot channel in here. Clay liner, if you have a recreational pond, you put a clay liner if you want to have water in it. It's a wet pond. Your clay liner usually about 2 foot thick, subject to hydrostatic pressure, trying to blow it up. So, you may have to dewater it if there's water there. You put your clay liner in, you put your water in, then stop the dewatering. Typical clay liner, you want to have a permeability of less than 10 to the minus 7 centimeter per second. Liquid limit greater than 50%, passing number 200 of 65 to 100%. Non-disturbed soils, minimum thickness of 2 feet. TCEQ, they allow you to have a PI of about 30 and higher for the clay liner itself. And so I like to see 50 if you can, but you can go as low as 30. There's a typical clay liner out there on a detention pond. We check it, we excavate with a backhoe, make sure the clay liner is 2 foot thick. You measure the thickness of it. Do not let the pond with clay liners sit empty for more than 14 days. If this pond sits empty without more than 14 days, if you're in the middle of the July, you're going to develop shrinkage cracks and the pond's going to start leaking water. So you don't want that to happen. Siltations. We have parts of Harris County, Montgomery County, Waller County. We have a lot of siltations, a lot of silty material. The water erodes them. That's a siltation of a channel in here. That's the detention pond out there that we're digging out there for development out there near Kingwood area. And they created a lot of runoff full of silt. The homeowners over here thought that this development here caused siltation of their channel and caused flooding of the houses here. So we have to go back and do some borings out there to find out the amount of silt on these channels. So we did some borings out there to determine the amount of siltation that were caused by the development. You know, the borings with the portable rig. Creep. If you got slopes that are gentle slopes, but they got fat clays, with time, soil creep is a slow downward movement progression of soil. Low-grade slopes, it's a slow deformation as a result of prolonged pressures and stresses. Expansive soils experience creep as a result of shrink swell cycles. And you can see roadway experiencing creep here. It's not a slope failure, but the whole thing is moving slowly. So it's called creep. You can see the poles kind of tilting. So in general, I know I went pretty quick here. It's the cost of your original geotechnical work. That's a change order if your slope fails. So it's, you know, you got to do a proper geotechnical work on projects. And we run into it in a lot of private projects where they really cut corners on the geotechnical part. They don't want to spend any money on them. But Harris County Flood Control's got pretty good guidelines for geotechnical guidelines for channels. We can't use them for private projects because they don't want to spend the money, but they got pretty good specs. If you got pictures of slope failures, I would appreciate you send it to me. That makes the project presentation interesting. This presentation is going to be on YouTube. You go Geotech Engineering and Testing YouTube channel. That's where it's going to be. There's going to be a program evaluation in here, what's called polling, and tell us what you think of the presentation. If you want to add something to it, let me know. Send me email. Let me know what you think. Contact for information, D.E. at geotecheng.com. Phone number is 713-699-4000. We're going to have a bunch of upcoming webinars. If you're on this list here, and we're going to put you on our database, you're going to get notices of these free webinars that we do. You're going to get a PDH hour for 1.5 hours on this presentation. Questions?